So in this video, we start looking at chapter 14, where we are going to begin an in-depth study of a notion that I first introduced to you on your exam. And I know that sounds a little bit of a weird thing to say. The reason is basically to see how adept we are becoming at manipulating the equations and definitions that we encounter to see if we are getting a skill or developing the skill of learning to parse new mathematical stuff on our own. And I always like to include one question like this because that way we are not wasting any time with our test. Right? The test is itself a learning opportunity, but also to sort of, I don't want to say set the curve, that sounds too mean, but it gives me a way of measuring a little barometer on the class, right? Like how is the class coming as a whole developing this skill of mathematical maturity? So let's start by recapping the definition. A homomorphism, phi from G to H, is a function such that phi of G1, G2 equals phi of G1, phi of G2. Now, before I was calling this like the isomorphism equation even, because it was the only context in which we had seen it so far. And an isomorphism was the same thing, except this function was required to be bijective. The time has come to be more precise. This property is called homogeneity. Actually, sometimes it even goes by other names, but that's fine for now. This is the one I think that we're likely to actually encounter. And so we were saying you are a homomorphism when you are a function between groups which is compatible with the operation, or if you like, it has this homogeneity property. There is no requirement that this function be injective or surjective. It simply is. For our first theorem for today, we are going to look at a familiar question. If phi is a homomorphism, then phi of E equals E, and phi of G inverse equals phi of G inverse. So before we jump into the proof, neither of which has a particularly difficult proof, we need to remind ourselves that this E is the E of the first group. Right? I wrote that it's a homomorphism, but what that means is that there's two groups here. This is the identity of E, and this is the identity of H. Now, we don't usually feel the need to spell that out in great detail, so we just don't write it. But it's important to know what we're saying, right? And understand what we're trying to prove. Similarly, this is the inverse of G calculated in G. This means apply phi to G and then get something in H and calculate the inverse in H. All right, let's see how we prove these. The proof goes by observing that phi of E is the same thing as phi of E times E, because anything times E is itself. Breaking the phi up, distributing phi, we get phi of E times phi of E. But now we are in H, right? Phi of E equals phi of E squared in H. And we know when we're doing a calculation in a group that if I had x equals x squared, I would just multiply both sides by x inverse and then get x equals E. The same is true here. E equals phi of E. All right, this proves the first part. For the second part, since phi of E equals E, how about we then take this E and replace it with GG inverse? Well, here I have phi of G inverse equals E. And now solving for phi of G inverse, we get phi of G inverse equals phi of g inverse, multiplying by the inverse of this guy on the left so that it goes over to the right. We see the desired equation. Okay, not so bad. These become particularly useful properties when doing calculations because basically every thing that we've done as far as group calculations involves multiplications and inverses. And this theorem essentially tells me that homomorphisms, being okay with multiplication, implies being okay with inverses. We got one more thing that we want to take a look at in this video, and this is the following definition. We need, actually, I guess, two parts of this definition. A conjugate of A is any element of the form XA X inverse for some X in G. We talked about the operation of doing conjugation. Now we just say if you are conjugated, right, by something, you are a conjugate of that something. Seems straightforward enough. Part two of our definition then, extending this slightly. Oops, sorry about that. I clicked a button and accidentally tabbed off. Let H be a subgroup of G. We call H a normal subgroup if H is closed under conjugation by G. Okay, I should probably unpack that a little bit. What I mean by that is if you have any element for any H in H, G H G inverse is also in H or any G in G. Because it would be silly to just say that you could conjugate by things in H, because H is closed under multiplication and inverses. So the extra property is that you can not only conjugate by things in H, but you can also conjugate by things in G. Okay, we are just about done with this section. I understand we're coming up on 10 minutes at this point, but in the spirit of finishing the section, so we could do this in one shot, I have one more theorem for us. It might make our video a little bit on the long side. The theorem goes as follows. Let phi G to H be a homomorphism. Then the kernel of phi, which is the set G in G such that phi of G equals E, is a normal subgroup. On the other hand, we have the image of phi. I think Pinter calls this the range of phi. That's what my memory is telling me. Image is the normal thing, which is just the set of all values in H that this thing takes on, is just a subgroup. Now the kernel is a subgroup of G, right? It's the elements of G in G, whereas the image is a subgroup of H. Okay. With this said, let's take a look at the proof. So for the kernel, the first thing we do is we prove that it is a subgroup. Well, phi of E equals E by theorem 1 of this video. And so E is in the kernel of phi. And so that's good. Next, we have to see that if G and H belong to the kernel, so does their product. Well, phi of GH is phi of G, phi of H by definition, which is E times E, since they're both in the kernel, which is E. So GH belongs to the kernel as well. And then lastly, if G is in the kernel of phi, I need to see that G inverse is in the kernel of phi. Well, phi of G inverse equals phi of G inverse, also by theorem 1. But phi of G is E by definition, or sorry, by assumption. It's in the kernel, and E inverse is E. So G inverse also belongs to the kernel of phi. Okay, next step is to prove that subgroup is normal. Well, this means that if G is in curve phi, that XG X inverse is also in curve phi for any X. Okay, so let's calculate what is phi of XG X inverse. This is phi of X, phi of G, oops, sorry about that, phi of X inverse, which is the same thing as phi of X, phi of G, phi of X inverse, because of the property we proved. Phi of G is the identity. Oops, there we go. Phi of X inverse, which is phi of X inverse, which is E. And therefore, XG X inverse belongs to the kernel of phi, as we wanted to prove. All right, we got one last thing we got to do, which is we have to prove that the image of phi, the image of phi is also a subgroup. And the proof of this is very straightforward, because what I need to do is see that E belongs to image of phi, but of course this is true because phi of E equals E, right? You know, this is the E of H, and so it's there. I need to see that if G and H belong to the image of phi, so does GH. And this is a little bit confusing only insofar as we need to understand what we're proving here. These elements are elements of the big group H. And so maybe I should change the notation for a little bit of clarity here. How about we use some different letters? How about we say X and Y in the image of phi implies XY in the image of phi. Okay, with this notation, if X is in the image of phi, then X is equal to phi of G for some G. And then similarly, Y is the image of some H. But then XY is phi G, phi H, and the definition of a homomorphism tells me that that is phi of GH. So XY is in the image, and we've knocked that one out. Lastly, I need to prove that if X is in the image of phi, so is X inverse. But of course this is true because X equals phi of G, so X inverse is phi of G inverse, which is phi of G inverse, again by the theorem 1. All right, and we have done it.